A very good day to our lecturer and everyone. My name is Adam and today our group will be presenting on our vibration analysis project. Before we begin, let me introduce my fellow team members. Delvis, Muhammad Anas Hakimi, Ayin Sofia, and Sarina Nubaya. To kick things off, I will be taking you through the introduction and the operational background of our scenario. Let's start by looking at our consultancy scenario. For this project, we have been retained as an independent vibration engineering consultancy firm. Our client mandate is to deliver a formal multi-phase machinery assessment and perform a comprehensive vibration analysis on a critical rotating shaft assembly. To achieve this, our study is broken down into two distinct operational states. First, condition A, which serves as our baseline. Here, we conducted baseline data logging into the newly installed healthy motor shaft assembly. Next, condition B, the degraded state. We investigated the exact same machinery after it developed an unknown operational fault over several months of service. Our core goal here is highly practical. We want to evaluate the overall severity using international ISO 20816-1 standards, isolate the root cause of this fault, and ultimately deliver actionable engineering solutions. With this objective in mind, let's move on to look at the physical setup we use. Moving on to the experimental setup, let's look at our hardware and instrumentation connection. We've broken our measurement chain down to 4 primary stages. First, for sensor integration, we utilize a PCB Piezotronics Triaxial Accelerometer. This was magnetically secured to the bearing housing, allowing us to accurately capture orthogonal dynamic data across 3 axes. Second, the data acquisition or DAQ part. Here, 3 separate low-noise BNC cables route those X, Y, and Z axis signals directly into our NI DAQ 4431 module channels. Third, for the speed verification setup, we deployed an X-TAC 461895 photo or contact tachometer to capture the real-time operational shaft RPM. And finally, the FFT calibration value. Obtaining a direct physical RPM measurement is crucial because it establishes the exact fundamental frequency, our 1 times RPM component, ensuring a flawless spectral analysis later on. That wraps up the initial hardware and scenario setup from my end. I will now pass the presentation over to Anas, who will get you to the next phase of our project. Thank you.
Okay, so for the sensor and mounting, what you're going to do is you have to connect a wire to the accelerometer. So as you can see here, the axis for x-axis is parallel to the bearing, y-axis is perpendicular to the bearing, and z-axis is facing upwards. And after that, what you're going to do is you start the machine, and then you're going to use the tachometer to measure the velocity in RPM of the shaft. And also the data at the computer will be taken. Next, what you're going to do is you do the same thing for second and third bearing and the case of the machine. And you have to make sure that the accelerometer is the same, the axis of accelerometer is the same as the previous one. Next, what you're going to do is you do the same thing for second and third bearing and the case of the machine. And you have to make sure that the accelerometer is the same, the axis of
Once the sensors in the motor shaft assembly is set up, it is now time to connect the microtech pin connectors to the NI data acquisition 4431. We must assign them according to the axis, which is X, Y, and Z. After that, connect the DAQ system to the laptop. You need to adjust the name, physical measurement, sensor class, physical unit, and sensitivity according to the DAQ's manual and project requirement. Note that for sensitivity, it has different values according to the axis, so we must assign them accordingly. Then, we need to set up the sampling rate to fast at 2000 Hz. After that, you need to run the test for 30 seconds. Once the test has been run, remember to save the results in TDMS format for MATLAB purposes. After that, you need to run the test for 30 seconds.
As the lead vibration analyst, I've translated our raw field data into actionable insights. We processed this in MATLAB using a 3-step workflow. First, we imported the files and applied a 1000 correction factor to scale raw voltage into velocity, ensuring ISO 20816-1 compliance. Finally, we used the fast Fourier transform FFT function to decompose our complex time waveforms into a clear frequency spectrum. Comparing our 8 data strings, the shift is undeniable. While condition A shows a stable baseline, condition B reveals a chaotic time waveform and, more importantly, near harmonic peaks at 2 times and 3 times running speed. This spectral shift is our smoking gun for internal mechanical issues. My analysis confirms 2 compounding faults: severe angular misalignment, evidenced by axial vibrations peaking at 5.892 mm per second, and mechanical looseness at bearing 2, evidenced by critical vertical vibrations of 5.062 mm per second. According to the ISO 20116-1 standard, we have reached zone D, the unacceptable range. The machine is at risk of imminent structural failure.
Next, let's move on to our conclusion and engineering recommendation. To begin our evaluation under ISO 20816-1 standards, our rig is classified as a Class 1 small machine since the motor is under 15 kW. Our formal finding is that the motor shaft assembly is currently completely unfit for continuous operation. Multiple measurement points have breached the unacceptable zone D limit of 4.50 mm per second RMS, which present a high risk of imminent structural damage if it stays online. Looking at our major velocity breaches, the axial direction hit a severe peak of 5.892 mm per second RMS against a thin wall structure. Meanwhile, the radial vertical shaking hit an unacceptable 5.062 mm per second RMS at bearing 2 and reached 5.106 mm per second at bearing 1. To understand what is driving these high numbers, our diagnostic analysis isolated 2 compounding mechanical faults working against the machine. The first fault is severe angular misalignment. We identified this through the high energy axial vibration reading of 5.892 mm per second RMS, which is putting destructive cyclic stress right onto the thin wall structure structural frame. The second fault is mechanical looseness at bearing 2. This is proven by the excessive vertical vibration peak of 5.062 mm per second RMS, which tell us that the structural foundation or anchoring components have relaxed and loosened up. To resolve these faults, our firm recommend a clear 4-step engineering action plan. First, we must restrict continuous operation and immediately stop using the motor shaft assembly to avoid internal component damage. Second, the client needs to perform a precision laser alignment between the motor and the driven shaft to directly neutralize the severe axial forces. Third, we need to inspect the foundation at bearing 2 and thoroughly retorque all hold-down bolts to eliminate mechanical looseness and stabilize the vertical shaking. And finally, as a quality assurance step, a mandatory post-maintenance verification test must be performed. Normal operations should only resume once a follow-up test confirms that all velocity values have dropped back below 1.80 mm per second, safely within acceptable class 1 tolerance for Zone A and Zone B. So that's all from our group. Thank you.